Okay, related rates. And you do need to write these steps, or at least know these steps, because these are going to be word problems, and you'll need to do them in these steps. On the test, I'm going to want to see the steps, okay? So you need to have this strategy for doing these problems. You're going to draw a picture, and these will be problems that you can draw a picture for. Number 2, you're going to write down what you're given. If you're given dr dt, if you're given the radius of this, whatever, you're going to write that information down. Step 3, you're going to write what you're asked to find, and it's going to be a rate. This is all about related rates, how fast things are changing, and you can only do that with calculus. Okay? 4, you're going to write a formula or equation that relates the variables. If you're talking about a sphere, it might be the volume of a sphere. It might be Pythagorean theory. There's going to be some equation. And if it's a formula that you don't know offhand, I'll give that to you. Like if it's the volume of a sphere, you just don't know that that's 4/3 pi r cubed. You're not going to know that. I'll give you that. But if it's something that you should know, then you need to know that. Okay, but I'm not expecting you to know those weird ones. Then you're going to have to use implicit differentiation to solve, because we're going to be differentiating with respect to time. So every variable, whether it's an x or a y or whatever it is going to have a dt tag on it. Just like we just had to put dy dx, we're going to have a dr dt, a dA dt, something. Everything's going to have a dt if you're taking the derivative. So we'll be doing implicit, and then we'll get an answer, and we'll evaluate. And that evaluate means, okay, now give me the answer in an answer form. Like if I asked you how fast the radius is changing, I don't want you to just write dr dt equals. I want you to say the radius is changing at 4.3 meters per second, whatever. So that needs to be there. Okay? Everybody good? Okay. All right. Now, at this point is when I would say, okay, take the sheet of problems that you have. And those of you that don't have it, got it right here, but it's little, so let's make it big so you can read this problem and write down what you need to. Okay. Certain calculus student who shall remain nameless hit Miss Barnes in the head with a snowball. You said awesome? Awesome. If the snowball is melting, snowball's melting at a rate of 10 cubic feet per minute, is that a big snowball or what? Yeah, well, I don't know. Okay, just go with it for me. All right, at what rate is the radius changing when the snowball is 2 feet in radius? And Ms. Barnes will be like collapsed when it hits. Okay, all right, so you're talking about a snowball and it's melting. So what is changing there? The radius is changing, but what else is changing? The volume, because this snowball is literally melting and getting smaller. So you want to think about that. The volume is changing. Is it increasing or decreasing? Okay, so the things that I would write down before I change this off the screen would be that it's melting at 10 feet per minute, cubic feet per minute. So write that down. Snow, just somewhere. It's not at the beginning of your problem. We're going to organize this. But for those of us that don't have the sheet. And then I would write this last sentence. At what rate is the radius changing when the snowball is 2 feet in radius? Okay, so this is all about rates, and so we're going to have DTs. All right, what is changing? What are we given that's changing that we know of? We said two things. but we know something is changing at a rate of 10 cubic feet per minute. What is that that's changing? The volume. So that's some given thing that we know. The volume is changing at 10 cubic feet per minute. All right, let's see how to organize this problem. Picture the big snowball being thrown. Well, you know, whatever. Okay, and I didn't have snow color, so it's blue. Okay, and the little red lines were, I think I did this picture for my 1325 in the spring, and they wanted the lines showing it was being thrown, so you have lines. All right, so that's the picture. Draw something that indicates, and it's not as important in this one as if you had a ladder problem which creates triangle. That's important. All right, number 2. That was when we were supposed to say what we were given. All right, we said the volume was changing at 10 cubic feet per minute. If it's decreasing, does it make sense that this is a negative? So dV dt, because it's a rate. It's a rate. So dV dt, because it's the volume, and it's negative 10. And I didn't put the units, but it's cubic feet per second. Okay, so that's our given. Third step, what are we asked to find? That's that last sentence that you wrote down. What did it say? Find the rate that the radius is changing. So if it's the rate of the radius changing, we're going to call it dr dt. Find dr dt when the radius is 2. So you need to write it like that. I'm going to go back to 100% so I can get a little bit more on there. All right, 4. We need an equation to relate all this so that we can put it in an equation. The volume of a sphere is 4/3 pi r cubed. This is one that I would give you. If you had one on the test that had to do with this, I would give you that formula. So you would write that. And number 5, step 5 says, okay, let's differentiate that. All right? So, what's the derivative of v? dv dt. It's like, what's the derivative of x? dx dt. Because everything's with respect to t. And so it'd be 1 dv dt. Equals. Now remember that 4/3 pi is not a variable, it's a number. So 3 times that is 12/3 or 4 pi r squared, because you drop that down 1, dr dt. Does everybody see that? Take the derivative of every piece. Then you look back at your given information. Didn't we say that dv dt was negative 10? So we're going to plug in negative 10 equals 4 pi r squared dr dt. What are we solving for? What are we trying to find? dr dt. So divide this stuff over here, and we've got dr dt. But we need dr dt at a particular value. What was the value? 2. When r equals 2, so plug in 2. And you have negative 10 over 4 pi times 4. And if you do that in the calculator, be sure that all of this down here is in parentheses to divide. Negative 10 divided by all that stuff on the bottom. And you should get negative 0.199. So just double check that you can do that in the calculator. Did y'all get it? If you didn't get it, it means something probably here with the dividing. And the last step would be to evaluate that, write it into an answer form. The radius is decreasing, because this is a negative, at a rate of 0.199 feet per minute. Are we okay with that? At least for the first one?
Are you going to have any, like, formulas
Like what formula would you need?
V equals 4/3 I,
I said that if I gave you a related rate with a formula that's not, that you would, it would be in the problem.
Okay.
I would give it to you. All right, so everybody's okay? All right, let's look back at the second problem. Make that a little big again. All right. Water flows at 8 cubic feet per minute into a cylinder with radius 4. How fast is the water level rising? That one's short enough that you might could write that whole sentence down and then have it. Water flows at 8 cubic feet per minute into a cylinder with a radius of 4. How fast is the water level rising? Let me know when I can go off of this page. Are we good? Y'all got it? Okay, let's go back over here. Okay. Me too. All right, so here's number 2. We've got a cylinder and water is flowing into it. And I wrote in red that the water level is really the height of the cylinder. We're going to use H, okay? And when you talk about, where's my actual problems? I don't have that written. Here it is. When it says water is flowing in at 8 cubic feet per minute, what is that that's changing? The volume of the water in the cylinder is changing. So it's the volume of a cylinder. So dV dt is 8. We're given that. Volume is 8. Well, the volume's not 8. It's changing at a rate of 8 cubic feet per minute. We're also given that the R is 4. Does that ever change? No. The radius of this cylinder is 4 forever. It doesn't change. So that's a given piece of information. And we're asked to find how fast is this water level rising. So find dH dt. If you used a different variable on your test, that's okay. That's not the issue. I mean, I'm choosing H, and that kind of makes sense to me. But if you said, I'm going to let Z be the height, and I'm going to find dZ dt or something, that'd be okay. But try to stay with what we're doing. All right. Volume of a cylinder. Pi r squared H. That's one that I would give you. I wouldn't expect you to just know that right off the bat. But that's step 4. And for this one, sometimes you want to differentiate before you plug in given things. Sometimes you can plug them in first. You've got 3 variables here. If you could plug in an R, that would help us out. And the R's not changing, so we can go ahead and put that in. So that's what I did there. So I end up with V equals 16 pi H. For this particular cylinder, that's what it is. Okay? And then we differentiate. dV dt, that's the derivative of V. The derivative of this, remember that 16 pi is a number. And it's an h to the first power. So the h disappears, and we have 16 pi dH dt. divide by 16 pi, that equals dH dt. Isn't that what we're looking for? How fast is the height of the water changing? So all you have to do is divide 8 by 16 pi, making sure that that gets divided as a single expression. Everybody get 0.159? And so then you would just write the water level is rising at a rate of 0.159 feet per minute. These are real life applications of this. Now, if I'm not sure when you'd need that, and nobody walking down the street is going to ask you to come up with that rate, but
in geography, we take a class called field geography. We go over everything you've learned in the last 5 years. We actually went down to the Brazos River and used this to figure out when it was raining how
really,
fast the water was
did you use
rising.
calculus to do it?
Yes, and the very
Awesome.
first question, we took a piece of PVC pipe, drove it in the ground, and then filled it with water and measured how fast it was draining out for soil absorption.
Well, awesome.
How fast the water gets
So when
absorbed.
somebody asks me if you're ever going to use this, I'm going to tell them when you go to A&M and you take a geography class. Awesome.
We did the same thing in ecology.
Ecology?
Yeah, ecology.
Very good. Awesome. I feel better now. We actually are doing some. All right, let's look back. And the rest of them are going, well, I'm never using that. All right, number 3. And you have to remember that these are problems that I created when I was teaching at Rikers. So, yeah. Some people will know the reference there and some will not. All right, the Rikers swimming pool. We don't really have one. We didn't have one, but a cone. And you really don't have cones for swimming pools. A cone with height of 20 and radius 5 is being filled by Mr. Koska with a hose which pumps water at the rate of 3 cubic meters per minute. When the water level is 2 meters, how fast is the level rising? All these are asking for instantaneous rates. At this particular instant, how fast is it changing? You can only do that with calculus. Okay? All right, so we get to draw. You want to write down or draw a cone that has a height of 20 and a radius of 5. You want to write down that water's going in at a rate of 3 cubic meters per minute. And how fast is the level rising when the water level is 2? Those are the key items that you want to write down. If you did enough of these, a cone problem is really pretty prevalent in calculus. That's why I've thrown one in here. Okay, can I go back to our page? All right. All right. Cone. All right, there's our cone. Okay, we have a height of 20 and a radius of 5. But what is different? Is the radius the same in a cone all the way down? No, it obviously gets smaller as we go, and the height at a particular place in the radius, the height is different as well. So we're going to need a way to relate the radius and the height because we've got too many variables there. This is one of those similar proportion things, if you remember from geometry, and probably most of us don't. But if we've got 2 similar triangles here, the radii can compare and the heights can compare. Or we could write it this way: r over h of the little triangle compares to 5 over 20 in the big triangle. And then I'm going to try to get r by itself. So what happened here? I just did cross multiplication. 20r equals 5h. Then I divided by 20, And so I have R is h over 4. That's a really common technique to get a radius or a height in terms of the other variables. Okay? All right. Let's see what we have. What did it say? Filling it, water's coming in at a rate of 3 cubic meters per minute. So do we agree that the volume inside this cone is changing at 3 cubic, whatever. I don't put the rates. The units. I forget that. We also know that the radius is 5 and the height is 20 up there at the top. Okay? We're asked to find how fast is the water level rising. So that's dH dt when the water is at 2 meters. So when it's right there, how fast is that level changing? That's what we're asked to find. Okay? We need the volume of a cone equation. 1/3 pi r squared h. 1/3 pi r squared h. But we have r in terms of h. So we're going to rewrite that with this h over 4 instead of the r. H over 4 squared. When you square h over 4, you get h squared over 16, and you multiply it by h. So we have 1/3 pi h cubed over 16. What happened here? How did I go to 1 over 48? What happened here? 3 and 16 on the bottom became 1 over 48. And I have pi h cubed. So you want to clean up your equation before you start to take the derivative. Okay? Then we'll take the derivative of it. Derivative of v is dv dt. The derivative of this, 3 times 1 over 48 becomes 3/48 pi h squared, because you drop one power down, and then you have to put the dH dt there. 3 times this number, okay? It's always exponent times that. All right, and then we can clean this up. That's what happened here. 3 over 48 becomes 1 over 16. That's just reducing it. Pi. Now I'm plugging in the things that I was given. I was given that dv dt was 3, and I want to know dH dt when h is 2. So at this point, I can plug in everything and solve for dH dt. So I get 3 equals, how did this become 1/4? 4 times 1/16, that's 4 over 16, that becomes 1/4. Pi dH dt, divide by 1/4 pi, so that's 3 over 1/4 pi. That's what happens there. And you should get 3.819. Make sure that you can get that. And then evaluate with water level is rising at a rate of 3.819 meters per minute when the level is 2. Are these a little better than we started? A little bit? Uh-huh. How far?
Like, where did your 16 go? Multiply it by the 3?
Right here?
No, on the equals 1/3 pi h cubed over 16.
Oh, 3 and 16, they're both on the bottom, so that became 1 over 48. Does that make sense? If you put it over here, if you had 1 over 3rd there, maybe that would show it better. All right. Okay, we're good? Last one on the page, and then we have one other one that we're going to do, but last one on the page. A stone is dropped into Lake Waco, causing circular ripples whose radii increase by 2 meters per second. When you have a rock, you see, you know how it does that. It has bigger circumference every time. How fast is the disturbed area growing when the outer ripple has a radius of 5? So maybe write down what you need out of that, and then we're going to go to the problem. What is changing what is increasing each time? The radius. So that rate is dr dt. That's going to be what we're given. Okay? Let me know when we can go to the page. Are we good? Okay. Lovely. So fun with the pictures. Okay, so there's our picture, and each time we're getting a different circumference, and the radius is changing. So we're given that dr dt is 2. That was part of what we were given. And the problem said, how fast is the area growing? How fast is the area growing? So that's a rate. So we're going to find dA dt. How fast is the area changing? dA dt when the radius is 5. Find dA dt when r is 5. What's the area of a circle? What's that formula? Pi r squared. So that would be one I'd probably expect you to know. Oh, come on. Should know that one. Okay, let's take the derivative of this guy. Derivative of that is dA dt. Derivative of this, 2 pi r dr dt. Remember, every time you take the derivative of anything, you're going to have a tag left on it. You're going to have a dt. And then it's just plugging in what you're given. You were given dr dt was 2, and you were given that the radius was 5. So we're just going to put those in and then multiply. So dA dt should equal 62.83 meters per second. Everybody get that? Yes, ma'am.
How many people are probably really bad?
2. I'm going to tell you all about that in just a second. But any questions on that one? Okay, the last problem was not on there. It's a ladder problem. It's a really common problem when you're doing related rates. If you have a ladder leaning up against a wall, and if it starts sliding, it's sliding and the base of the ladder is going that way, and this part's going down this way, and it often asks, how fast is it sliding when it's a certain height? So we're going to do that problem. I don't have that one typed for you, so you don't have to feel bad about not having that print. Not that you felt bad, but
I did.
you did? You felt really bad? That's good. I like that. And I want you to really take note of the artwork. I really had fun drawing on my tablet because we started embellishing, and
That took some time.
it did. It really did. And take, the lovely little squares for the windows, the rectangles. Of course, I have a drawing tool at the bottom right here, so that came out. But the tree and the cat. Of course, the cat is as tall as the door. This perspective is a little off. I don't know. I'm not an artist. Okay. So, yeah, but I had fun. Okay.
Do we get credit for drawing?
Well, I really do like those. So, it could be helpful. I don't know. All right, a 13-foot ladder is leaning against a house. So that's important, that the ladder's 13 feet long. The base of the ladder is slipping away from the building. So the ladder's doing this and the bottom slipping away at a rate of 5 feet per minute. Okay? Yeah, hope nobody's up there on the ladder. Yeah, that's true. Find the rate at which the top of the ladder is sliding down at the very instant that the bottom is 12 feet from the base of the house. I would really study this problem if I were you. Okay? Move it back up. Sorry. What shape did we have with a ladder leaning against a house? Triangle. And is it a right triangle? Yes, because the house makes with the ground a right angle. So Pythagorean theory is going to come into play. What is that theorem? A squared plus B squared equals C squared. That's going to be what we use. I would expect you to know that. Okay? If you had that problem. All right. So, number 2 on our steps. Let's see if I can get more space here. All right. Why did I call that dx dt? Let's look at the picture. If you drew the picture, this is the part. You don't have to draw the house, but this is x. Think about it on an xy grid. Here's x, here's y, and we were told the bottom of the ladder was slipping. So x is changing. So that'll be dx dt. So we have dx dt is 5 when x is 12. That's what we're given. dx dt is 5 when x is 12. I don't know what this is. Okay. When x is 12, we're going to need to know what y is. So I wrote that here. When x is 12, I need to know what y is. And so 12 squared plus y squared equals 13 squared. 144 plus y squared equals 169. Subtract, take the square root, you get y is 5. Some of you may know that that's a special right triangle and it's always a 5, 12, 13. But maybe not. Might not be that on the test. Okay, so we needed to know that. We also need to write down, what are we supposed to find? What were we supposed to find in that problem? Yeah, how fast is the top of the ladder changing? Well, that height was y. So we're supposed to find dy dt when x is 12. Okay, we know dx dt. We're supposed to find dy dt. All right, here's our equation that relates those. Number 4, the step. X squared plus y squared equals 13 squared. Okay, so you'll write that, and then we're going to take the derivative of that. So when you take the derivative of that, remember we're doing implicit differentiation with respect to t. So 2x dx dt plus 2y dy dt equals 0. Okay? At that point, we have all those pieces to plug in. We know x is 12. We know dx dt is 5. We know y was 5 because we found that. And what are we trying to find? Dy dt. you should get to a point where everything gets filled in except the one variable that you're trying to find. So when you do that, you get 120 plus 10 dy dt equals 0. Subtract the 120 and then divide by 10. You get dy dt is negative 12. That should make sense because the ladder's doing what? It's coming down. It's decreasing. So that should make sense that it's negative. And then the ladder is sliding down at a rate of 12 feet per second. You don't put the negative in that last part of the answer. When you write sliding down, that takes care of the negative. Does that make sense? A little bit. I would go home when you go home sometime today, and I would maybe play the video again. I would work through it, print it out, go through the problem. Try it, okay? Any questions on that?
You spell
Up? Okay. How far? There? Is that good? Did you get it? Okay.